NEC 250.30 requires that to grounding electrode system be installed at each service, building or structure, and it shall include a grounding electrode conductor run to the electrical equipment. NEC 250.32 requires that the equipment grounding conductor shall be connected to the grounding electrode conductor at the service. NEC 250.24 C requires that a corner grounded delta system shall have at least one grounding connection at or near the midpoint of one phase leg of the transformer. Corner grounding provides a ground fault path for the secondary side. A grounding conductor is connected from the neutral point of the delta winding to the equipment grounding conductor, or EG, and then to the grounding electrode system. Other code-compliant choices include center tap grounding and high leg delta. Center tap grounding requires a separate center tap transformer with a grounded neutral. It provides a ground fault path through the grounded neutral. High leg delta requires a transformer with a high leg winding that is 1.732 times the voltage of the other two windings. The neutral point is not grounded. Ground fault protection is provided by a ground fault detection device. For a single 230-volt three-phase pump load, corner grounding the delta is the simplest and most cost-effective code-compliant solution. There are additional considerations. Ensure that all equipment is properly grounded. Install a ground fault protection device to protect against ground faults. Perform regular inspections and maintenance to ensure the safety of the installation. When dealing with a 480-volt Y to 208-volt delta transformer setup, especially when the secondary serves a single 230-volt three-phase pump, ensuring proper grounding on the delta side is paramount. The primary goal is to establish a reliable ground fault path, which is essential for safety and code compliance. Several methods can achieve this, each with its own advantages and considerations. Firstly, let's explore corner grounding. This method involves grounding one of the phase conductors of the delta winding. In practice, this means connecting one of the three phase lines directly to ground. This connection serves as the reference point for the system voltage. Corner grounding offers a straightforward approach to creating a ground fault path. When a fault occurs, such as a phase conductor coming into contact with a grounded surface, the fault current has a clear path back to the source, triggering of a current protection devices like circuit breakers or fuses to trip and to energize the circuit. This helps prevent electrical shock hazards and minimizes equipment damage. NEC 250.24 C mandates at least one grounding connection at or near the midpoint of one phase leg of the transformer in a corner grounded delta system. This requirement ensures that the ground connection is effective in providing a low impedance path for fault currents. Secondly, center tap grounding involves using a transformer specifically designed with a center tapped winding on the delta secondary. The center tap is then grounded, creating a neutral point for the system. This method effectively splits the delta winding into two equal voltage sections, with the grounded center tap serving as the neutral reference. Center tap grounding offers a balanced approach to grounding, providing a stable neutral point and a reliable ground fault path. When a fault occurs, the fault current returns to the source through the grounded neutral, again triggering overcurrent protection devices. However, center tap grounding requires a specialized transformer with a center tapped winding, which may not always be readily available or cost-effective. Thirdly, the high leg delta configuration is another grounding option. This setup uses a transformer with a higher leg winding, which has a voltage that is 1.732 times the voltage of the other two windings. The midpoint of one phase is grounded, creating a neutral point. The high leg, also known as the stinger leg or wild leg, has a voltage to ground that is higher than the other two phases. While the high leg delta system can be used, it's essential to understand its characteristics and potential drawbacks. The high leg poses a safety concern because it has a higher voltage to ground, which can create confusion and increase the risk of electrical shock if not properly identified and marked. Additionally, single-phase loads must be carefully connected to avoid the high leg, as using the high leg for single-phase loads can result in equipment damage. The high leg delta system relies on a ground fault detection device to provide ground fault protection, as the neutral point is not directly grounded. This device monitors the system for ground faults and trips the circuit breaker when a fault is detected. The effectiveness of this approach depends on the sensitivity and reliability of the ground fault detection device. Now, let's consider the specific scenario of a single 230-volt three-phase pump load. Given this limited load, corner grounding the delta emerges as the simplest and most cost-effective solution for code compliance. It eliminates the need for a specialized transformer or a complex ground fault detection system. Corner grounding provides a direct and reliable ground fault path, ensuring the safety of the installation and the protection of equipment. To ensure a safe and reliable installation, several additional considerations are important. Firstly, all equipment, including the pump motor, must be properly grounded. This means connecting the equipment grounding conductors, or EGs, from the equipment back to the grounding electrode system at the service. Proper grounding minimizes the risk of electrical shock and provides a low impedance path for fault currents. Secondly, installing a ground fault protection device is highly recommended, even with corner grounding. This device can detect even small ground faults that may not be sufficient to trip standard overcurrent protection devices. By detecting and interrupting these small ground faults, the ground fault protection device can help prevent equipment damage and reduce the risk of electrical fires. Thirdly, regular inspections and maintenance are essential to ensure the continued safety and reliability of the installation. Inspections should include checking the integrity of grounding connections, testing the operation of ground fault protection devices, and verifying the overall condition of the electrical system. Any issues identified during inspection should be promptly addressed to maintain the safety and performance of the installation. Let's dive a little deeper into the code requirements for grounding, particularly focusing on NEC 250. The National Electrical Code, or NEC, provides comprehensive guidelines for grounding electrical systems to ensure safety and prevent electrical hazards. Understanding these requirements is crucial for designing and installing a compliant and safe electrical system. NEC 250.30 outlines the requirements for grounding electrode systems at services, buildings, and structures. It mandates that a grounding electrode system be installed at each of these locations and that it include a grounding electrode conductor that runs to the electrical equipment. The grounding electrode system serves as the primary connection to earth, providing a low impedance path for fault currents. Common grounding electrodes include ground rods, ground plates, metal underground water pipes, and concrete encased electrodes, often referred to as UFA grounds. NEC 250.32 addresses the connection of the equipment grounding conductor, or EG, to the grounding electrode conductor at the service. The EGC is the conductor that connects the non-current carrying metal parts of equipment, such as enclosures and motor frames, back to the grounding electrode system. This connection ensures that any fault current on the equipment has a direct path back to the source, allowing overcurrent protection devices to trip and de-energize the circuit. NEC 250.24 C specifically addresses the grounding requirements for corner-grounded delta systems. It requires that at least one grounding connection be made at or near the midpoint of one phase leg of the transformer. This requirement ensures that the ground connection is effective in providing a low impedance path for fault currents. The location of the grounding connection is critical for ensuring that the ground fault path is as short and direct as possible. In addition to these specific code requirements, there are several other important considerations for grounding electrical systems. Firstly, the size of the grounding conductors must be adequate to carry the available fault current. The NEC provides tables that specify the minimum size of grounding conductors based on the size of the overcurrent protection device protecting the circuit. Secondly, grounding connections must be made securely and reliably. Loose or corroded connections can increase the impedance of the ground fault path, reducing the effectiveness of the grounding system. Grounding connections should be made using approved connectors and methods, and they should be regularly inspected to ensure their integrity. Thirdly, the impedance of the ground fault path should be as low as possible. A low impedance ground fault path ensures that fault currents can quickly and easily return to the source, allowing overcurrent protection devices to trip and to energize the circuit. Factors that can increase the impedance of the ground fault path include long conductor runs, undersized conductors, and loose or corroded connections. Let's further examine the practical aspects of implementing corner grounding. When corner grounding a delta transformer, it's crucial to select the appropriate phase conductor to ground. Generally, any of the three phase conductors can be grounded, but it's important to maintain consistency throughout the electrical system. Once the phase conductor is selected, it should be connected to the equipment grounding conductor, or EG, using a properly sized grounding conductor. The EGC should then be connected to the grounding electrode system, ensuring a direct and low impedance path to ground. The grounding electrode system should comply with NEC 250.30 and consist of one or more approved grounding electrodes such as ground rods, ground plates, or metal underground water pipes. When installing ground rods, it's important to drive them deep enough into the earth to reach a low resistance soil layer. The NEC specifies minimum depths for ground rods, which vary depending on the type of soil and the local conditions. Ground plates should be buried below the frost line to prevent damage from freezing and thawing. Metal underground water pipes can be used as grounding electrodes if they are electrically continuous and in direct contact with the earth for at least 10 feet. In addition to the grounding electrode system, it's also important to ensure that all metallic enclosures and equipment are properly bonded together. Bonding involves connecting the metallic parts of equipment together to create a common ground potential. This helps to minimize voltage differences between equipment and reduces the risk of electrical shock. Bonding should be done using approved bonding jumpers and connectors, and all connections should be made securely and reliably. When dealing with a 480-volt Y to 208-volt delta transformer, it's important to consider the voltage transformation ratio when selecting grounding conductors and overcurrent protection devices. The voltage transformation ratio is the ratio of the primary voltage to the secondary voltage. In this case, the voltage transformation ratio is 480 volts divided by 208 volts, which equals approximately 2.3 to 1. This means that the secondary current will be approximately 2.3 times the primary current. Therefore, the grounding conductors and overcurrent protection devices on the secondary side must be sized accordingly to handle the increased current. It's also important to consider the potential for harmonics in the electrical system. Harmonics are distortion of the sinusoidal waveform of the voltage and current. They can be caused by nonlinear loads such as electronic equipment and variable frequency drives. Harmonics can cause a variety of problems, including overheating of equipment, increased energy losses, and interference with electronic devices. To mitigate the effects of harmonics, it's important to use harmonic filters or other mitigation techniques. Harmonic filters are devices that are designed to block or reduce the flow of harmonic currents. They can be installed at the source of the harmonics or at the point of utilization. Let's turn our attention to ground fault protection devices. Ground fault protection devices are designed to detect and interrupt ground faults. They work by monitoring the current flowing in the grounding conductor. If the current exceeds a certain threshold, the device trips, interrupting the circuit and energizing the equipment. Ground fault protection devices are typically used in circuits that supply sensitive equipment or in areas where there is a high risk of electrical shock. There are several different types of ground fault protection devices available, including ground fault circuit interrupters, or GFCIs, and ground fault equipment protection, or GFEP. GFCIs are designed to protect people from electrical shock. They are typically used in residential and commercial applications such as bathrooms, kitchens, and outdoor areas. GFEP is designed to protect equipment from damage caused by ground faults. They are typically used in industrial and commercial applications such as motor control centers and switchgear. When selecting a ground fault protection device, it's important to consider the sensitivity and the response time. The sensitivity is the amount of current that is required to trip the device. The response time is the amount of time that it takes for the device to trip after a ground fault is detected. The sensitivity and the response time should be selected based on the specific application and the level of protection that is required. Finally, let's emphasize the importance of regular inspections and maintenance. Regular inspections and maintenance are essential for ensuring the continued safety and reliability of the electrical system. Inspections should include checking the integrity of grounding connections, testing the operation of ground fault protection devices, and verifying the overall condition of the electrical system. Maintenance should include cleaning and tightening connections, replacing worn or damaged components, and testing the operation of all safety devices. By performing regular inspections and maintenance, you can identify and correct potential problems before they lead to accidents or equipment failures. Grounding systems are an absolutely essential component of modern electrical systems, as they serve as the first line of defense against electrical shock hazards and equipment damage. A well-designed and properly maintained grounding system provides a safe and reliable path for fault currents, allowing overcurrent protection devices to quickly and effectively de-energize circuits in the event of a fault. The importance of regular inspections and maintenance cannot be overstated, as these practices help to ensure that the grounding system continues to function as intended over time. Remember that electrical work should always be performed by qualified and licensed electricians who are familiar with the NEC and local electrical codes. These professionals have the knowledge and experience to design, install, and maintain electrical systems safely and effectively.